Okay, thank you very much, Naveen, for that nice introduction. So, as Naveen says, I'll be talking about young galaxies forming the high-redshift universe. The purpose of the talk will be to give you not really an overview, but show you a little bit about what we're doing in terms of the study of galaxies at this epoch. It's great to be here at Riverside, by the way. It's my first time here, so I'm very happy to be here. Okay, so over the last few years, dramatic progress has been made in observing galaxies to greater and greater distances. This little diagram schematically shows this current efforts to push to greater and greater distances, you know, as a function of time, pushing out closer and closer back to the Big Bang. Now, as we think about doing this, studying these high redshift galaxies and trying to push earlier and earlier into the universe, the question comes, why do we go about doing this? Why do we care to find galaxies at very early times? And one of the reasons that we're interested in doing this is really the epoch where galaxies were born in large part. It's where the halos, the collapsed dark matter halos of these, of sort of normal L-star galaxies, normal typical galaxies formed. Things like the Milky Way or whatever, where their dark matter halos initially assembled. And this can be seen by looking at the following diagram, showing roughly some sort of rough volume density versus the mass in the dark matter halos. And I call your attention to this 10 to the 12 number here, this position, this horizontal position, because this corresponds to the mass, rough mass, of a slightly greater, something like the Andromeda galaxy, like our neighboring galaxy. It's a little bit more massive than the Milky Way, but it's sort of a typical galaxy. And if you want to think about how the volume density of these things changed across cosmic time, you can see that at redshift 10, the volume density was very low. And as you go back to redshift 3 corresponds to basically 2 billion years after the Big Bang. So over the first 2 billion years of the universe, the collapsed dark matter, which make up galaxies, assembled. Which means that early in the universe, galaxies were in rapid assembly mode. They were rapidly building up. You know, just like you imagine a city, all the buildings rapidly getting built up. So studying galaxies in the early universe are interesting for that reason. Another reason that studying galaxies is interesting is it's when the universe was reionized. We have this nice little schematic here, nice little diagram from Brant Robertson showing a brief history of the universe, starting with the Big Bang, this rapid cool down period until the epoch of recombination. Then the universe went through a period called the Dark Ages, where the universe was filled with lots and lots of neutral hydrogen. The universe is fairly homogeneous, but even though it's homogeneous, some regions were slightly more dense than other regions, and those overdense regions pulled in matter from around them to become more and more overdense until we came to a situation where the first stars, first galaxies formed. And these things are thought to reionize the universe, to bring about the reionization of the universe. So studying sources in this region, studying galaxies in this region, can potentially give us insight into how the universe was reionized. So now let me bring you to my outline after that brief introduction. Here I'll show you what I'll talk about today. I'll start out with a basic introduction about how do we find galaxies in the distant universe. What kind of technology or whatever do we use to do that, and techniques. How do the properties of galaxies change across cosmic time? What drives galaxy buildup? How far away we can, to what redshifts we can identify galaxies spectroscopically. We can measure redshifts with spectroscopy, and do galaxies drive cosmic reionization? So let me start out with an introduction. How do we find galaxies in the early universe? So I've already just shown you this diagram showing you how far with various facilities we've been able to reach back in cosmic time to observe galaxies. And the design of this figure is actually useful because it emphasizes that our ability to find galaxies in the distant universe is significantly driven by technology, telescopes, instruments, etc. our ability to see further and further away is fundamentally technology driven. And so that's basically the point. So what are the key instruments and telescopes for finding sources in the distant universe? Well, there's many different facilities, but I'll just throw up these here again, where one of the workhorse instrument and telescope for finding many of the most distant galaxies in the universe has been this WIF3 camera, this instrument on the Hubble Space Telescope. This has really been an important instrument. There's also other things which have been useful. The IRAC instrument on the Spitzer Space Telescope, which gives us information at redder wavelengths, and a wide variety of ground-based telescopes, which are also useful in identifying very distant galaxies. And what is the key thing about all these things? Well, it's the infrared sensitivity. Why is infrared sensitivity important? Because light from these very distant stars, distant galaxies, is getting redshifted across the history of the universe. The light is getting redshifted as the universe expands, and the light is getting redshifted from UV wavelengths to near-infrared wavelengths. And so near-infrared sensitivity is really key to make progress on very distant galaxies. So to give you an illustration of the dramatic advances that have been made over the last few years, I'm just going to show you a little illustration about how some of the data has improved over time. I've started with this illustration of the Hubble ultra-deep field, showing you a NICMOS image of the Hubble ultra-deep field. 144 orbits of data were taken over this region of the sky. 144 orbits basically corresponds to, on the order of 1.5 weeks of telescope time on the Hubble Space Telescope. And on this you could see 2 redshift 7 galaxies. There's also a third here, but these are galaxies which were seen with the NICMOS instrument, which was taking data back in 2004, 13 or 14 years ago. Now there's a new instrument available called the WIF3 camera, which was installed in 2009 on the Hubble, and with that camera, even slightly more data was taken. Not too much more, but on the same order, but roughly same amount. But you can see that the dramatic improvement in the quality of the data. These redshift 7 galaxies that we previously knew of, we can now see at much higher signal to noise. And in many regions where we could barely detect any sources, now there's, I guess that region you don't see so much of an improvement. Here, you can see large numbers popping in. Where you can see many, many more galaxies in going from the old data to the new data. So you can see you could push much, much fainter. And in terms of the overall numbers, we went from maybe saying 7 redshift 7 galaxies to 100 redshift 7 and higher galaxies. Now, redshift 7 corresponds to roughly 750 million years after the Big Bang. So that's the epoch that I'm showing you. Going from 4 objects known 750 million years after the Big Bang to 100 objects known 750 million years after the Big Bang. So how do we identify these distant galaxies, you might ask? How do we know which of these objects on the images are very distant? Well, we take advantage of a technique called the Lyman break technique. And this technique takes advantage of the fact the universe is filled with lots of neutral hydrogen. The neutral hydrogen absorbs light blueward of Lyman alpha to bring about what's called a Lyman alpha break, such that when you view it through a bunch of broadband filters, there's a bunch of filters on the Hubble that you can view this object with the spectrum that looks roughly like this, and then you end up getting images that look like this. You get nothing, no detection at all the bluest wavelengths, and then a detection at the reddest wavelengths with a blue continuum. And the nice thing about having data like this is the place where the spectrum moves from no detections to detections is an abrupt break. And it tells us the redshift of the source. It tells us how far away the source is when this galaxy emitted light. So we can actually just we can actually read off how far away it is, effectively. However, you can also find galaxies at many other points in cosmic time using an analogous technique. This shows you a movie showing how a star-forming galaxy would look at many different redshifts. And you can see that it's systematically shifting from having a break across the bluest filters all the way to having a break across the reddest filters. And you can see that, basically this break is slowly moving across the filters that you would view with Hubble. And so if you select objects that show this break across different sets of filters, you can selectively identify galaxies which existed at different points in cosmic time. And then by measuring their properties, you can try to construct an evolutionary scenario about how galaxies have changed across, cosmic time. So where do we find these galaxies in the distant universe? Well, the way that people generally try to do this to get the most information is people generally use a wedding cake strategy. Wedding cake strategies are used to look for galaxies, but they can also be used to look for other things like quasars, or any potential domain. I mean, people use this effectively wedding cake strategy, and the wedding cake strategy basically causes us to start with to have a hierarchy of different search fields where you have a very, very sensitive search field which doesn't cover much area. So you have a very small area field where you are very, very sensitive. And then you have, as you go down several tiers, a very wide area search field where you're not especially sensitive, but you cover lots of area. So sensitivity moves in one direction and area moves in the other direction. And so how does this work out for finding galaxies? Well, for finding galaxies, one has a similar type structure. One can end up having a very wide area search field, in this case using various ground-based telescopes. One conception of this uses the ultravista field, which covers 1/2 square degrees, and maybe a UDS field. These are different parts of the sky, and here's how big they are relative to the full moon. So you take data with various ground-based telescopes over these regions and look for high-redshift galaxies. So that's one tier in the survey. You can also look for sources in a deeper tier. And one deeper tier which is popularly used is with HST. And that's the candles known as the candles program, which has effectively some of the deeper data is taken within things like the ultravista and UDS search field, and some of these search tiers lie outside these fields. And this allows us to find fainter sources which are slightly more common in the universe. So because these fields are more sensitive, we can find fainter sources. Then there's even deeper level tiers, which, for example, the Hubble Ultra Deep Field is a very long exposure with a Hubble Space Telescope, and it covers a very small area. And with this field, you can find much, much fainter sources. And to go even deeper, there's now been this new program called the Hubble Frontier Fields program, which combines the power of very long exposures with the Hubble Space Telescope, much like the UDF, the Hubble Ultra Deep Field, with gravitational lensing. And with gravitational lensing, you take advantage of the fact that massive objects like galaxy clusters in the distant universe can act as magnifying lenses to make these fainter sources even brighter. And so you combine gravitational lensing with long exposures with the Hubble Space Telescope and other facilities. And so that can complete a nice wedding cake survey, where you essentially try to look for galaxies over a wide dynamic range in properties. So how many galaxies can you find in the distant universe? And I'll just show you some results that we had from basically about 2 years ago, where we searched for galaxies that are different epochs. Redshift 4 is 1.6 million years after the Big Bang or so. Redshift 5, 1.3 billion years after the Big Bang, 3,000 objects. Redshift 6, 900 million years after the Big Bang, with 900 objects in this probe. Redshift 7, 500 objects after the Big Bang. Redshift 8, maybe 200, and now Redshift 9 and 10. Now Redshift 9 and 10, with 40 objects, at Redshift 9 and 10 is basically 400 to 550, something like that, million years after the Big Bang. That's very early in cosmic time, and yet we're still able to find large numbers of sources. And so, just to give you an impression of the fact that these sources found with these different different search programs have different properties, I just show you the following diagram, showing you number I show you galaxies found at redshift 7. Redshift 7 is 550 million years after the Big Bang. In this compilation, more than 700 galaxies are found. These are the number versus luminosity. And what you can see is the total number of sources found per luminosity. And what you can see is large numbers at the bright end, the very high mass end. You tend to find most sources over the widest area fields. And then as you go to lower and lower luminosities, you see that the sources are being provided by different tiers in the wedding cake survey. So basic at the faint end, maybe you're finding most of the sources of the Hubble Frontier Fields. Intermediate, mostly with candles, etc. So this is, now we can step back further in cosmic time, not just looking at things at redshift 7, but also looking at things at redshift 9 to 10. Redshift 9 to 10, again, we're talking 450 to 550 million years after the Big Bang. And here shows you the numbers versus luminosity. What you can see is that there's, all these data sets are contributing some numbers. And so amazingly, with current data sets, we're able to do quite well. So how far away can we look back in cosmic time in trying to find galaxies? What is the current record holder? Well, the highest redshift galaxy that people generally believe to have found, based upon photometric evidence, is this, what's known as this redshift 11 galaxy. That's been found over a field called Goods North. Goods North is has an area of 150 square arc minutes, which is much smaller than the size of the full moon. And at redshift 11, we're talking about, I think, getting close to maybe 400 million years after the Big Bang. And why would we think that it might be at redshift 11 or so? Because of the photometric evidence, and later I will talk, if there's time, about the spectroscopic evidence. Here shows you some of the photometric evidence. This shows you the flux of this object, measured flux of this object versus wavelength. Here are some of the images of the object. The object is at the center of the postage stamp, and what you can see is that it starts to show up prominently at 1.6 microns, shows up prominently at 4.5 microns. With Spitzer, the telescope has a much smaller diameter, so the image kind of blows up in appearance. And if you look at this, you can see that it seems to show an abrupt break at basically 1.5 microns. Now, if you ask what 1.5 microns, how that compares with the Lyman alpha break, that suggests a redshift of 11. Okay, now that we've thought about how to find galaxies in the distant universe, what can we learn about their properties? What can we learn about how their properties have changed at early times? Well, we have a number of tools or telescopes we can use to do this, to explore this question. And I show these in the context of a simple toy spectrum of a redshift 8 galaxy. Redshift 8, again, is 600 to 650 million years after the Big Bang. And I show this as a function of wavelength, and here you have a toy spectrum. So you can learn about it from HST, providing data of the bluest wavelengths, and you can, at the red end, looking at things with ALMA, a big array of telescopes that exist in Chile. And ALMA can tell us about dust emission and other properties of these distant sources. So this is dust, this is mostly stars. And so HST we can use to learn about maybe the star formation rate. With Spitzer, we can hope to learn about things in this regime, which is the rest frame optical. And that can tell us about maybe some of these emission lines that you see here, etc. So there's lots of tools that we have to look at and try to understand the physics of these objects. So what is okay, so there's many things you can look at. Let me start with something that's pretty basic, which is the UV luminosity function. So this is the luminosity function in the UV. And I showed my own results. I mean, many other results from other people have been obtained, but we'll just, for simplicity, just show my own. This shows you the volume density on this axis of galaxies, and this shows you the luminosity in the UV. This is the bright end, and this is the faint end. And so what I show here is the determination of the volume density of galaxies as a function of luminosity at redshift 10, 9, 8, 7, 6, 5, and 4. And what you can see is that basically as the universe goes from very high redshift, early points in time, to later times, galaxies are becoming more luminous, and they're showing evidence for becoming brighter. More luminous and potentially showing a higher volume density with cosmic time. And so you can see that galaxies are building up. One reason that it's interesting to look in the rest frame UV is the rest frame UV light probes very hot stars. And probing hot stars tells us something about their star formation rate because they don't live very long. So one thing that people use the UV luminosity function to look at is what is the star formation rate density of the universe? How does the density of star formation vary, of star births, of bursts of stars vary across the history of the universe? And I show this here, plot this here. This shows the star formation rate density plotted against basically the age of the universe here. This is how old the universe is. This is expressed in terms of redshift. And these are these new points. These are some of the points that I just showed you. And what you can see is this, that this thing sort of evolves as such, that the universe grows in star formation until eventually it turns over and then falls off. The thing about this star formation rate I've shown you, this is affected by dust. I've just shown you the star formation rate that can be directly observed. Now, dust can obscure UV light, absorb it, etc., to keep us from seeing young stars. And so we have to worry about that. Fortunately, there's this new facility called ALMA, and this ALMA facility which gives us insight into dusk-obscured star formation, which allows us to see light that's been absorbed by stars and then re-emitted at far infrared wavelengths. And so by using constraints from ALMA at millimeter wavelengths, people have been able to come up with some constraints on how the star formation rate density evolves with cosmic time. Here I show you one determination of this obscured star formation, taking this into account. At lower redshift, constraints have been obtained with other facilities like Herschel, with the Spitzer Space Telescope, etc. I'm not going to go into a complete history of this, but this is what we've been able to do. And ALMA has been able to allow us to make some progress here. Another area that we've been able to make progress over the last number of years is how big galaxies are as a function of cosmic time. What are the physical sizes? How big are galaxies as a function of cosmic time or redshift? Now, this is early in the universe, this is late in the universe. And if you try to measure the physical size of these galaxies at a fixed brightness for galaxies, what's been found is that the sizes go from being very large to becoming increasingly small at early times, with the size basically varying inversely with the 1 plus the redshift of the object. Now, this isn't so surprising because early in the universe was much more, everything was much smaller. The universe had higher density, and all the collapsed objects also had higher density. And because they had higher density, things of a fixed mass were physically smaller. And being small, and that basically corresponds to what we see here. And there's a general result that shows that the sizes of galaxies roughly scale as some percentage, small percentage of the size of the collapsed objects in the universe. Another result that we've had by looking at galaxies across cosmic time is to look at the strength of the line emission. And I show this in terms of the equivalent width. The equivalent width tells us essentially how much continuum light we need to integrate over to match the amount of line emission. So on the one hand, we have light coming from stars, which is continuum light, shows a nice continuum shape. And on the other extreme, we had line emission. Now, line emission comes from hot stars, young stars, etc. Lots of things like that. What we find over the history of the universe is going from low redshift to high redshift that the equivalent width is continuing to increase with cosmic time. It's continuing to increase with redshift, decrease with cosmic time. Cosmic time runs this way. So it's continuing to increase with redshift. over the history of the universe, which suggests that at very high redshifts, the galaxies are looking more and more like being dominated by these very strong spectral lines, and not so much by sort of a smooth shape. So how are we able to look at these emission lines? Now, at low redshift, relatively close to us, a lot of these lines have been studied very extensively using direct spectroscopy by using things like the Keck's telescope and the Mossfire instrument, by using the HST grism, etc., to essentially get a spectrum of various lines. This shows you lines taken with HST grism at redshifts around close to redshift 2, which is 3 billion years after the Big Bang. These are things that you can see. And this is the O3 line, where you've looked at it with the grism. When you go to very high redshifts, we don't currently have a tool to look to get a spectrum of these lines, a very high resolution spectrum of these lines. The best we can do is to measure the strength of these lines by taking images of these, from photometry, by taking images of these galaxies in various broadband filters, just like various filters. And this shows you a spectrum of a galaxy at redshift beyond 8, showing you flux versus wavelength. You see basically the flux measurements at very blue wavelengths. Suddenly, and the blue line shows the model. The red points show you measurements. Here, basically, you see something like a Lyman break. Then you see it continues out to redder wavelengths. And then you see this jump at this wavelength. And this jump is likely due to this O3 line. It's this O3 line I just showed you in the last plot, and this O3 line shows a big jump in the spectrum. And it's thought to be elevated due to O3 emission. So we have evidence for this O3 emission, but it's only in a very low resolution spectrum. To give you an illustration of how these strong lines could affect a spectrum, I'm going to show this illustration here, where we show flux versus wavelength. We show a model spectrum and then various photometric measurements done with HST and with Spitzer. This is at redshift 8, 600 million years or so after the Big Bang. Let's see how this spectrum changes as we increase the line emission. More line emission. So we go from this, more line emission. You can see that in this case, this band here called the 4.5 micron band is being significantly boosted by line emission from these likely hot stars in these galaxies. And you can see this emission just in the Spitzer data. You can also look for other lines in these galaxies, not just O3, but the H-alpha Balmer line. And that can be seen here. So I've got the same thing. I'm showing something very similar. Now it's at redshift 5. Again, something like 1.4 million years after the Big Bang. And you can see the spectrum of this object, where this line, where you can see that a lot of the lines just sort of fall along the continuum, but this one is boosted due to this strong line here, this H-alpha line. And so we can measure, again, in this case, the equivalent width of this object, the strength of this line, from the photometry. Now I'm going to show a little, so what should we make of these strong lines? How strong are they? Now I'm going to show a little toy diagram. And what I'd like to show to you is how strong are these lines relative to our naive conception of how strong these lines are, how strong these lines are from the UV continuum. So we'll just take a simple-minded estimate of how strong these lines should be, and that's indicated by this thing here. This is, again, supposed to be fairly qualitative. Here's some expectation from some normal models. And some of our results have been suggesting that the equivalent width of these galaxies in H-alpha, depending on whether things are red or blue, are somewhat in excess of these expectations for the normal models. And here are some results at somewhat higher redshift. Now, these results here are from the H-alpha line measured from IRAC. I showed you how we can measure H-alpha from IRAC in the previous slide from the Spitzer Space Telescope. Now, this effectively also gives us information on this other parameter, I'm going to quantify this in terms of this other parameter called C-ion. C-ion is plotted here on this axis, and what this C-ion gives is the ionizing photons per UV photon. It basically tells us how much, in the ionizing photons, now ionizing photons produce line emission. So ionizing photons go out there and they hit neutral hydrogen, they excite the neutral hydrogen, and then when it recombines, it produces line emission. So this ionizing, so effectively, the line emission over continuum emission is basically this: ionizing photon per UV continuum photon, which is what I was talking about. It's the spectral hardness. And what you can see here is this whole plot, again, suggests that normal galaxies and red galaxies show elevated number of ionizing photons per UV photon. So given what we see in the UV, these things are putting out large numbers of ionizing photons. And why is it interesting? That's interesting for us because if galaxies are producing large numbers of ionizing photons for every UV photon we observe, galaxies will be very efficient at potentially reionizing the universe. We know the universe needs to be reionized. These things can potentially, this means galaxies can be potentially efficient at doing the job. Now, this elevated number of ionizing photons per UV photons may be a bit strange, and if it is in fact the case, then there's several different explanations for it. Why might there be an elevated number of ionizing photons per UV photon? Well, it could be due to the fact that these stellar evolution models may be a little non-conventional. There's been a lot of models that include binary stars, lots of binary stars in the universe. Binary stars can cause individual stars to produce more ionizing photons for a longer period of time. Maybe it's due to a top-heavy IMF. Now, what is a top-heavy IMF means that galaxies have, top-heavy means that there's a large number of high-mass stars, a lot more high-mass stars than you might expect from a conventional model. High-mass stars put out lots and lots of ionizing photons. Then bursty populations. So maybe the star formation rate in a galaxy is varying up and down rapidly. And if it's varying up and down rapidly, during these bursts of star formation, you may have lots and lots of formation of hot stars. And those hot stars may produce lots and lots of ionizing photons. Yes?
What about dust? It seems like dust would obscure the UV continuum you see, but the lines are at a longer wavelength.
Yeah, that could be true. And so I'm just showing something very simple here. No, that's definitely a big effect, and we correct for that when we do these estimates. The challenge in making these, and that's actually an important challenge for these estimates, because we need to know the dust properties in order to make these estimates properly. So sometimes, depending on what we assume regarding the dust, if we assume the dust it has an attenuation, it has a certain effective attenuation as a function of wavelength that, say, looks like this or like this or like this, we can end up getting different results. So there is some model dependence. Some of the inferences we make do, in fact, and it's a very insightful question you asked, some of the inferences we make do depend very sensitively on what we assume about dust. And so this is going to be an important uncertainty to resolve going forward. And in fact, I guess Irene Chevet is again is looking at this question again using some of the MOSFIRE data from the big MOSDEF program. So there's a lot of important work going on this, and it's going to try to look again at how dust affects these inferences. Okay, so let's see. Okay, I think I'm 25 minutes in. Okay. Okay, so now let's move on to another topic. So now let's talk about the topic of what drives the buildup of galaxies. What explains how galaxies evolve with cosmic time, particularly in the early universe? And I'm going to try to frame this in terms of the evolution of the UV luminosity functions, the luminosity functions in the rest frame UV. And so I showed you that basically the presentation of these measurements of luminosity functions showing you how galaxies change from redshift 10 to redshift 4, showing you how they change. And I think it's interesting to think about why this might be the case. And what I'm going to try to show you is that you can try to understand this and model this in a very simple way. You can model this basically using gravitational collapse. In the early universe, a lot of the evolution, I would argue, is dominated by things that collapsing onto initial overdensities in the universe. And as these things get larger and larger and larger due to gravitational collapse, you can try to explain a lot of the evolution. So let's try to explain the evolution of these UV luminosity functions using just using what we understand about gravitational collapse. And what do we understand about gravitational collapse? We can follow the evolution of these dark matter halos. So dark matter halos are dark matter, you just use gravity. You just use gravity, and you use what you know about dark matter, and you just follow the evolution of how fast these dark matter halos or collapsed objects are growing as a function of cosmic time and in the spectrum of structure. So let's look at the halo mass function. I showed that at the beginning of my talk. Let's just think about that. Let's think if we can understand this evolution using the dark matter halo mass function. Let's assume the mass to light ratio is fixed at all points in cosmic time and at all masses. Same mass to light ratio for everything. And so let's just do that. And so we have these observations. Now let's try to do that with the dark matter halos. And we can do, so we just show this. This shows you the dark matter halo, luminosity functions constructed from the dark matter halos using a fixed mass to light ratio. And let's see if we can explain the other. And so let's see if we can match these things. So let's try to get these things to look like these things. Well, one thing you might notice is that the redshift 10 point is much too faint. And the redshift 4 point maybe is not too bad. The redshift 4 point is not too bad. The redshift 10 point is too faint. So maybe the mass to light ratio, maybe the mass to light ratios at early times are lower. Maybe a fixed amount of mass is producing more light at early times. And let's just implement that. So let's just make high redshift halos brighter. Just sort of assume that whatever mass they have is getting converted into light more efficiently. And one way of accounting for that is just basically the fact the universe is denser at early times. And if the universe is denser, the dynamical time is going to be less. Maybe mass is getting converted into stars more efficiently. And so let's just implement that. OK, so we just implemented that. And so now we have things look a lot better. But you can now see that this candidate luminosity function is much too steep relative to the actual luminosity function. That the rate of change in the volume density as a function of luminosity is much steeper in the models than in the observations. And so how might we understand that? Well, one way of understanding that, and it's been a conventional way of understanding that, is that the community thinks that star formation is not super efficient in low-mass galaxies. And that's because low-mass galaxies experience feedback or a negative feedback effect from supernova. Supernova can cause explosions and cause gas to move outside of low-mass halos. So if the halos aren't supermassive, they can lose mass. And this can cause us to cause these things not to be efficient at forming stars if they're low mass and the supernova are blowing the gas out. So that can cause the lower mass objects to be systematically fainter. And so what we can do is implement a recipe where we say the mass to light ratio is going to be higher for fainter galaxies due to supernova feedback. Supernova feedback is going to keep these things from having a lot of mass. And so we'll do that as some power of the mass. So let's do that. OK. Things are looking better now. But now if we do the comparison, you see that in the model, there are far too many bright galaxies in the model relative to the observations. And what could explain that? Well, what can explain that is that eventually, once you go to a very high mass thing, it's thought that you could end up creating supermassive black holes in the centers of the galaxies. These supermassive black holes can be AGN, and the supermassive black holes, when they accumulate too much mass, start to put out huge amounts of energy. This huge amounts of energy at high masses can cause it to heat the gas, and if the gas is heated, it can't form stars. Another thing is that high mass galaxies can also have lots and lots of heavy elements. Heavy elements form dust, and dust can cause the UV light not to be seen. So that both of these effects can cause high mass objects to not be easily observed. And so we might think that we might want to cut off these UV luminosity functions because of these effects. And so we can just implement a recipe like that. So basically we need to implement a cutoff, the bright end, quenching. Quenching is from AGN, high mass, supermassive black holes, and maybe dust extinction. Just implement it as a fixed stellar mass and do this. And then we have that. And now let's compare the luminosity functions. Okay, things look pretty good. So the purpose of this, so what we've done here is we've just started with the dark matter halos. The dark matter halos are just a product of gravitational accretion of the collapse of matter onto an object. We've implemented a few simple physical, sort of semi-physical motivated prescriptions where we have the efficiency of starvation varying as 1 over the age of the universe of the Hubble time. So at high redshift, there's lower mass to light ratios. And we've implemented some other physically motivated prescriptions where we basically have, and this is just where we have the mass to light ratio being systematically higher for the fainter galaxies due to supernova feedback, and the mass to light ratio being dramatically higher above some fixed mass at the high mass end due to quenching or dust extinction. That's illustrated in terms of the following diagram, which compares essentially shows the dark matter halo. That's typically been used to explain why there's a difference between the dark matter halo mass function and the galaxy luminosity function, which looks like this, where you see that the shape doesn't match at either the low mass end or the high mass end. And so what I'm trying to show is that by just a simple implementation of physical prescriptions, you can try to understand a lot of what's going on with galaxy evolution. What's kind of scary about all this is it's possible that even a simple model like this might be able to predict a lot of the things that we observe in the future with the James Webb Space Telescope. The James Webb Space Telescope will be launching in a few years, will be a much larger telescope, be much more sensitive, and allow us to push much further into the history of the universe. But it's possible that just a simple model like this may be able to explain a lot of this. And it's just basically gravitational accretion built up at early times in the universe. So a lot of you might be thinking that maybe a lot of what I've been saying doesn't have a strong physical basis, and maybe I'm making a lot of inferences. Maybe a lot of things I think are very distant galaxies aren't so distant. Maybe we think we see a Lyman break where there isn't one. So it's useful to test these things by obtaining spectroscopy, by using various telescopes to obtain spectroscopic observations and verify that what we're saying isn't completely crazy. And so how can we go about getting spectroscopy on these distant galaxy samples to learn about the properties of galaxies? Well, the typical tool that's been used to do this is the Lyman alpha emission line. And I've illustrated it here with a nice diagram showing you flux versus wavelength. And this shows you a bit the Lyman break, then you have the strong Lyman alpha emission line, and then you have sort of a bit of a slight continuum. And this Lyman alpha emission line is very useful for measuring redshifts, as illustrated in the following diagram, where you see the fraction of objects with Lyman alpha emission that's readily detectable, that's 25 angstroms, versus redshift. And this shows you the number of objects, again, versus redshift. You can see it's between 35 and 50%. So if you get a long exposure on a galaxy, which is fairly sensitive, for about maybe 40 to 50% of the cases, you can expect to detect Lyman alpha and verify the redshift directly. Now that's very nice, that we can verify the redshifts, the distances to these objects very directly. Now as you go beyond redshift 6, now this is 900 million years after the Big Bang, the numbers start to fall dramatically. The fraction starts to fall until redshift 8, where it's not clear that we are able to, that any of these objects show Lyman alpha. So why is there a change beyond redshift 6? Now, the reason is thought to be that as you go beyond redshift 6, we're reaching into an era of the universe when the universe wasn't completely reionized. The universe started to contain increasing amounts of neutral hydrogen. Beyond this point, the universe contained lots and lots of neutral hydrogen. Now, what does neutral hydrogen do? Neutral hydrogen can cause lines like Lyman alpha to resonantly scatter. So the Lyman alpha line will hit the neutral hydrogen, bounce all around. And if it bounces all around, then it becomes very, very difficult to observe. And so when you go back to early and earlier times, you start to have so much neutral hydrogen that maybe you can't find Lyman alpha at all. So how can we go forward? We'd like to get redshifts of systems. We'd like to get redshifts of systems, and we don't want to be inhibited by the fact that the universe is increasingly neutral. So what can we do? Well, one potentially promising way is to target those sources which are putting out which we expect to have huge amounts of line emission. Sources which are ionizing huge numbers of neutral ionizing huge numbers of neutral hydrogen atoms within their gas, and these ionized neutral hydrogen atoms will be producing Lyman alpha. So where can we find objects that are producing intrinsically huge numbers of Lyman alpha photons, which you could hope to potentially observe despite all these challenges? Where are some objects where we could potentially do this? One place we could potentially do this is in galaxies which show strong line emission at other wavelengths. Because if we see strong line emission at other wavelengths, then maybe we can also see Lyman alpha. And so one place that it's good to look is to look for those objects which are particularly bright in O3, which have a particularly bright O3 line. And we saw how to maybe do that. We went out and remember earlier in the colloquium, we went out and looked at a bunch of objects where flux versus wavelength we saw based upon the IRAC lines that we could potentially get the strength of O3. And so these things might be really interesting to look at. And so what we did is we looked at the entire CANDLES program, which I showed you earlier, that the entire program, which doesn't quite cover the size of the full moon, but which still has a lot of area, and we identified the brightest 4 galaxies which show strong O3 emission. And so what happened when we looked for Lyman alpha in those galaxies? Well, we had the following good luck. Here's a spectrum of one of the objects we looked at. Had a very nice O3 line here, the very nice Lyman alpha line here. Flux versus wavelength. Here, there's a lot of other noise in these spectra, but you can see a very nice Lyman alpha profile. This line is known to be asymmetric. Here's the appearance of this in the 2-dimensional spectral data. This is dispersion direction, and this is spatial direction. This is dispersion direction. You can see this very nice Lyman alpha line. It had a redshift of 7.73, which puts it back at basically, I think, around 650 million years after the Big Bang or so, 700 million years after the Big Bang. We also followed up a number of other sources. So that was a press release because that was a record breaker at the time. We also followed up some other sources. Here's another source we followed up. Again, we see a very similar asymmetric line, Lyman alpha, 2-dimensional spectrum, dispersion direction, spatial direction. And again, this was a record breaker made for a press release. In fact, all the objects, all the 4 brightest galaxies we followed up in the sample all showed Lyman alpha and suggested that by targeting sources which were had strong O3 emission and were very bright, that we could find Lyman alpha. So this is an exciting thing that we were able to do. What are some other approaches that are useful going forward? Another approach that may have some promise is actually targeting sources with ALMA. Now I showed you this big ALMA facility, this set of basically millimeter dishes in Chile, this big facility, €1.5 million facility earlier. And I said that it told us something about allowing us to measure dust emission from galaxies. Well, it can also be used to do other things. It can also allow us to look for strong interstellar medium cooling lines from galaxies. it could potentially allow us to look for sources. And even though there's been a lot of results in the literature which haven't resulted in super bright lines, some galaxies have shown, there's been a lot of galaxies which haven't been so bright with ALMA. We recently found this source which showed very prominent emission in this interstellar line called ISM line, cooling line called C+, here. And it points this object to having a redshift of 6.85, indicating that it's at a very, very high redshift. And we did this, again, using something different than Lyman alpha. And it's another way we can go forward to trying to spectroscopically confirm these galaxies in the early universe. Another way of going about doing this, beyond the two different techniques I showed you, is to also look for continuum breaks. Now, we expect galaxies to show continuum breaks due to the Lyman alpha break that I talked to you about. That's how we identify the galaxies. And this is useful because, again, a lot of these galaxies may not show Lyman alpha in emission. So we need to find some other way to confirm the redshift. And so what's an interesting object to look at? Well, an interesting object to look at, well, we'll get to that in a bit. How do we go out and measure these continuum breaks? Well, we can use the HST GRISM. The HST GRISM, essentially what it does, and it basically takes light we see with HST, it disperses the light according to its wavelength along some direction, and then we image it with HST. This gives us a spectrum of these objects, and in this spectrum we look for a break. HST GRISM is really the best tool we have available to do this because it's outside the Earth and it's beyond, so that we don't have to deal with the bright Earth's atmosphere. So which object did we observe with this? We observed this very, very distant galaxy I talked to you about earlier within the Goods North field that I talked to you about being at redshift potentially 11. And this is the object, again, earlier in the thing, and we observed this. And what happened? Well, we got this very tantalizing spectrum for the source showing you, here's flux density versus wavelength. It's pretty noisy, but you can see, again, here's a two-dimensional spectrum, these dispersion direction, the spatial direction, some evidence of flux here, and again, there's evidence of a break here. It's again, we would like it a higher signal to noise, but it looks very indicative, and it does suggest a redshift 11.1. So we're hoping, we've applied, and we keep on hoping to get some more data on this, but it may be something that we may need to wait until the James Webb Space Telescope to confirm it completely. Okay, now finally I'm going to say something about cosmic reionization. I'm running toward the end of my time, so I will try to go through this relatively quickly. Do galaxies drive cosmic reionization? So we have a lot of information on cosmic reionization from studies of Sloan quasars, absorption studies of Sloan quasars. We know that basically, here's a spectrum of a very bright quasar in the sky. We know due to the presence of these Gunn-Peterson troughs that the universe is showing an increasing amount of neutral hydrogen, suggesting the end of cosmic reionization. That cosmic reionization is ending around redshift 6, basically 900 million years after the Big Bang. We know something about the duration of cosmic reionization from the Planck measurements. Planck gives us a constraint on the Thomson optical depth. The Thomson optical depth gives us an integral constraint on the electron density between the cosmic microwave background and the present day. It tells us how long the universe has been reionized. And if you put all this together, it suggests that cosmic reionization began around redshift 10 or earlier, midpoint around redshift 8, and completing around redshift 6. So the question we have is whether galaxies can drive the reionization of the universe, whether galaxies can explain the universe being reionized. And in order to determine this, we need to count the number of ionizing photons coming from galaxies. And we tend to do this by multiplying 3 different factors. We start with one factor giving us the total number of UV photons the galaxies are emitting. How many galaxies in the UV continuum galaxies are emitting at some point in cosmic time. Then we multiply that by a conversion factor that takes us from the UV continuum photons to the number of ionizing photons, or Lyman continuum photons. So this is a conversion factor which goes from UV continuum to ionizing photons. And then finally, we have to correct this for the fact that not all ionizing photons escape from galaxies. So that's called the escape fraction. Now that's a very uncertain number, and this is a, oh, let's see, okay, this is a very uncertain number. And there's a wide variety of estimates for it. People like Brian Sienna are world experts on this parameter, and lots of work is going into it. It's very uncertain, but let's assume 10%. And to think about whether galaxies reionize the universe, let's have this funding goal: 0% here, 100% here. Can galaxies reach the funding goal of photons to reionize the universe? So let's first start with the bright galaxies. The galaxies we can see within fields like the Hubble ultra-deep field. And let's just frame this question at redshift 6, 900 billion years after the Big Bang, and just think about this. So this is volume density versus luminosity. These are constraints on the volume density versus luminosity at redshift 6. And let's just integrate the photons and see how many ionizing photons. So we start with counting the number of UV continuum photons, then convert that to ionizing photons using some normal conversion factor and a normal F escape. And now if we do that, and we ask in galaxies reionize the universe, we get, oh, here we go, we got 20% of our funding goal, ionizing photon goal, to reionize the universe by redshift 6. Now, presumably there's, now you might think, where else might we get ionizing photons? Well, we can get them from fainter galaxies down here. These galaxies down here, presumably they exist. We might not observe them in the Hubble ultra-deep field, but they exist, and they probably provide ionizing photons. So we could try to extrapolate and include those as well. Now, one could just do the extrapolation, or one could try to estimate their volume density in another way, and in a slightly more direct way. And one way of potentially doing that is to use the Hubble Frontier Field program. Now, the Hubble Frontier Field program potentially allows us to go much fainter than what we see in the Hubble ultra-deep field by, again, combining the power of long exposures with gravitational lensing. And so from this, you can potentially identify many, many fainter sources in the Hubble ultra-deep fields. And here's sort of one potential way, the luminosity of individual sources. These are all very uncertain luminosities versus redshift. And this is an attempt to use all 6 clusters and derive the luminosities of individual sources. Showing in this line, black line here, shows you what you can get with the Hubble ultra-deep field. And here's potentially a prior study showing you where one of those previous galaxies might have been. And now let's just take all the galaxies here that are at redshift 6 and look at what luminosities they might have. Here's the limit again by the Hubble ultra-deep field. These are faint and these are bright, and we have many galaxies which are potentially fainter. And so what we can do now is try to come up with, okay, we have to zoom through the talk now because we're running to the end, running out of time. So we can try to figure out what these sources imply for the total volume density of faint sources in the universe. And so it's useful to take advantage of size constraints. I won't talk about this in detail, but we can measure the sizes of the fainter sources and then use them to estimate the volume densities. We can take advantage. We can correct for uncertainties in the gravitational lensing models. We use gravitational lensing. The amount of gravitational lensing for an individual source is uncertain, so we need to model that. And so we can also deal with that. And if we do that, we can come up with 68, 95% confidence intervals on the log volume density as a function of luminosity. And so we can add the photons from these very faint sources by just integrating them up as follows, just integrating these all up to the center of the probability distribution, and then figure out how much this helps us in reaching our funding goal. So let's go from here and add up the fainter sources. And if we do that, okay, now we're to 45% there. Now, what else can we use to reach our funding goal of reionizing the universe? We can potentially account for the fact that these star-forming galaxies produce potentially a higher number of ionizing photon per UV photon like some of the earlier results suggest, these results may have suggested. If that's true, then we can go from 45% to plausibly 100% and reionize the universe. Now, of course, all this depends on the uncertain escape fraction, which we're still waiting. We're anticipating much heroic work from Brian going forward, but a lot of this is really uncertain depending on the escape fraction. And so we can anyway. There's more work going on in these ultra-faint sources where we can derive luminosity functions at many different redshifts. With James Webb, a lot of these sources that we see that look like this with Spitzer Space Telescope, we will be able to get nice spectra like this. So things now, you might think, oh, this is kind of a crap spectrum. In the future, we can get something that looks a lot more like this, rather than 5 or 6 resolution elements. And this is like what we see with Spitzer. With these very high redshift galaxies, like the redshift 11 galaxy, where we had this very low signal-to-noise GRISM spectrum, in just a half an hour, we can get this nice spectrum with the James Webb. I showed you these very nice lines that were detected with ALMA for one source. We also have a second source that I didn't show you. And going forward, we'd really like to expand that and get more sources with these lines from ALMA. This will be very useful because it gives us information on the kinematics of these faint sources. And that's something we also be able to do with James Webb. Basically, I'd like to acknowledge a large number of people who have made this work possible, including various funding organizations. Rensk did the great stuff with the line emission with ALMA, lots of other work being done, also postdocs. Again, lots of galaxies promise exciting things with James Webb. Simple models based on gravitational collapse can use us to understand a lot of the buildup of galaxies. Star-forming galaxies seem to be putting out lots and lots of line emission and show evidence for lots of ionizing photons. Lots of progress is being made on getting spectroscopic redshifts with MOSFire, ALMA, and also with HST GRISM, and based upon the constraints we have on the going to faint galaxies using the Hubble Ultra Deep Field and Frontier Field work, combined with these high amounts of ionizing photons from galaxies, suggests that galaxies, very, very likely drive the reionization of the universe. So thank you very much for your attention. I apologize for going. I think this colloquium I used 63 minutes of time, so apologies for that.